Hello all, I'm Mara Johnson-Grow. I am the onboard or offboard outreach officer for Expedition 395. We're here today with sedimentologist Dustin Harper to give you a bit of a tour around the JR and talk about Expedition 396. So to get us started, for those of you who don't know, Expedition 396 is one of the expeditions by the International Ocean Discovery Program, or IODP. The IODP has been drilling all across the world in various oceans for over 50 years. It's an international scientific collaboration with scientists and technicians from around the world. The work that the IODP does helps us understand the oceans better and sort of what's going on in the Earth's history and what will go on in the Earth's future. This work will be extended into the future. We're already thinking another 50 years out as we continue to research, explore, and communicate the science that we're discovering. So this all happens aboard the JR, that's the JOIDES Resolution. It's a 470-foot ship that we've been using since the 1980s. And with this ship, we're able to drill down hundreds of meters below the ocean floor to gather core samples to learn about the Earth's history and sort of what was going on in the past, look for fossils, various sediment layers, all this kind of cool science that's going on. So this ship has done hundreds of expeditions all around the world. And currently we're floating around the North Atlantic, a few hundred miles or kilometers off the coast of Norway for Expedition 396. And our main goals for this expedition are to look at magmatism and how magmatism is linked to climate change, particularly at this period in Earth's history called the Paleocene-Eocene thermal maximum. And this is about 56 million years ago when the Earth was a really hot place, kind of like the changes that we're experiencing today. They had similar changes back then, although theirs weren't caused by humans, of course. So To talk about this expedition today, we've got with us our scientists aboard the JOIDES Resolution. Dustin, are you there with us?
Yeah, hi, can you see me and hear me? Yeah. Good?
Great. I'm not sure we can hear you there.
Okay, I'll try and speak loudly, because we're outside right now. We're actually right above the
So we
drill
seem to
rig
have
floor.
an issue with our sound here. We'll try to get it sorted
Okay.
out. Just a second. All right. Okay, we should be good. Great. Dustin, do you want to give us a tour and tell us a little bit about what's going on in Expedition 396?
Yeah, absolutely. You can hear me now.
Yeah, sounds great.
All right, great. So it's a little loud out here. We're standing on the bridge deck right now, right above the drill rig floor behind me here. And you can see the long stand of pipe that's going down through the middle of the ship. And right now we're drilling at about 2,000 meters of water depth. So that's equivalent to roughly right around a mile. And we're rotary coring. And when the core comes up, it comes out of the drill string. And the drillers pull it out and they bring it down to the here on the catwalk. And the catwalk is this little boxed up room down here, and we'll go down there next. One other thing just to point out up here would be we have some lifeboats here just in case of emergencies. So they'd be a little bit tighter than the JOIDES Resolution, but hopefully we don't have to use those ever. So now I'll just take you guys inside towards the science officer. And we have our key instrument here, the espresso machine, used quite often, most mornings. And this is also where we can hang out and have some snacks, talk science with the co-chiefs. And if you want to follow me down, I can take you guys downstairs to the core lab and the catwalk. And on the way down, we have a little wall filled with pictures of our loving pets from home. Give us a little smile every morning on the way to work. So when core comes in, that's the drill floor there. And it comes in a lot, and the technicians lay it out and cut it into sections, about 1.5 meter pieces here on the catwalk. And from there, they bring it in and they laser engrave it, each little section, so we don't lose track of the pieces. And we start running it through different physical property scanners that measure all different kinds of things like density and magnetic susceptibility. And we also X-ray the pores before they make their way over here to the splitting room, where Beth and Jessica are currently cleaning up some core ready to be split that we just drilled. Here we have some pieces of various basalts. These are extrusive magmatic rocks at the bottom of the seafloor. So once core is cut, we bring it out here and we lay all the core out. Here is the sampling table. So this is usually we're really busy around noon when the two shifts cross over and we decide which samples we want to take immediately. And from there, the other half comes over to where we work, the core description table. So you can see we have a couple cores out right now, and we have various hard rock here. Again, these are basalts. So these are layers of lava flows that we're drilling. And on top of those basaltic layers, we often will get little layers of sediment as well. So here, some clay that we recovered at the top of this site. And Weimu here is doing a little imaging. I'll let her talk about the shill.
Hello, I'm Weimu. I'm from University College Dublin. I'm one of the shipboard sedimentologists, and one of the goals for sedimentologists is we partly describe the pole, but also to image the pole. And this one is section half imaging logger. So we can take high resolution images of all the poles we retrieve.
Okay, yeah.
Yep.
Thanks, Weimu. So I'll move around here. Now we have a couple more physical properties loggers here. And I'll walk back to Sarah, who is working on the microscope currently. Look, do you want to talk a little bit about what you're looking at?
Sure. Hello, I'm Sarah Lambert. I'm an assistant professor at University of Utah. And so we are looking at thin sections, so very, very thin section of rocks that we prepare on board on the ship. And we are looking at them with microscopes to confirm the mineralogy that we estimated from the core description table over there. So what we can do is looking at this image live. Here, so for example, here we have a nice grain of biotite, and biotite is very easy to identify with the microscope because it's changed color. This is called pleochroism. Here, and so we can take nice picture of interesting features that we see in the mineralogy of the rock to put them in the scientific publications that will come out of this expedition.
Great, thanks, Sarah. So next, I will just talk a little bit about what I'm doing. So I'm more focused on these sediments, and I'm looking at these intervals that Mara mentioned, like the Paleocene-Eocene thermal maximum, and using them, these warming events as analogs or case studies for modern climate change to assess the sensitivity of the oceans and the environment to massive amounts of carbon release. Besides that, here is Sayantani, who is currently flagging some samples for
My geochemistry analysis of the salt, and I want to do some carbonate analysis in some sediments. So yeah, we have some very beautiful vesicular basalt. So, and if you can see, the colors are changing from here and then change from here. So these are one, you can say, a flow unit. So we study all the chemistry of hard rocks and the sediment to make a good electrostatic technique. So I'm sampling now.
Thanks, Sayantani.
Thank you.
So besides that, shipboard life is pretty interesting. We work 12-hour shifts, 7 days a week for 2 months. And we switch off with our shift counterparts at midnight and at noon. And we cross over and discuss what we found and discuss some of the implications, while also co-authoring some preliminary reports. So I'll switch it back over to Sarah, who's going to talk a bit about some of the rocks we have out on the description table.
Yeah, so the interesting part of the job on the boat here is we always work as a team. So I'm actually in the same team than Dustin, and our main job is to describe the rocks that we receive basically. So we have actually several examples here, and Dustin's expertise is in sedimentary rock, and my expertise is in hard rock. And so you can see a large variety in this, small selection of samples. And for instance, when we actually got this box the table, I was particularly excited about that because those rocks represent basalt that are formed very, very early in the process. So they are going to give us a lot of information about the source of the magma that produce this lava. So this is very exciting. And so we are going to do, after this expedition, a lot of chemical analysis on these rocks.
Yeah, thanks, Sarah. So one way we recognize certain boundaries and changes in climate would be through changes in the sediment that's being deposited. So right here we have a not very old sediment as an example, but you can see there are some changes in color through this, and those changes in color are often associated with climate change. So as the climate changes, you have the change in the environment, and that's going to lead to deposition of different types of sediments, and sediments with different chemistry as well. Next, I will switch it over to Reed Shearer, Professor Reed Shearer, who works on diatoms, and Hank Brinkhouse, who works on dinoflagellate cysts. You guys want to chat about your science at all?
There are no fossils in this book. We came to the fossils. We have no fossils. Next site, we will have fossils. Now we use these fossils to interpret climate history, and a variety of different fossils. Some of them algal fossils, and some of them the things that eat the algal fossils. Diatoms are makeshells out of biogenic silica and natural glass, and have a lot of different species. But in the sediments we've covered so far, we haven't got them. We're looking forward to getting some in the next site. And I'll let Hank talk about his Dinoflagellate, which is quite useful in this. But we're anticipating it to be quite useful in this.
Yeah, well, folks, we are here for a really, really cool purpose, and that's the theory that these volcanic rocks that you see lying over here actually led to an incredible amount of CO2 in the atmosphere, so that it got really warm. And one way to test that it really was warm is to look at these fossils. And as Reed has alluded, there are so many of these fossil groups. One of them is the Dinoflagellate, which are really, really cute little things that can kill you. Maybe you know of certain harmful algal blooms. Those are typically Dinoflagellates. They don't die.
Red tide.
The famous red tides. And what happened 55, 56 million years ago, that it got so warm that one of these red tide fossils, it dominated the entire planet, from the North Pole to the South Pole. And that is one of the reasons why we want to learn more about this sudden abrupt warming, and also how the ecosystem, at that time there were no humans yet, although fascinatingly, that particular episode, when you go dig in the mountains of Montana, you'll find the first mammals. The first mammals begin to look like that. All of the modern mammal families come about when this volcanism is done in this warm place. So that's why everything is connected. And that's why we all work together here to get the data to come together to understand what happens when the world gets really warm, as it is doing right now. Here's the social relevance. Thank you, Mr. President.
Thanks, Hank. So I think Mara, you said that we would field maybe a few questions now. Happy to take the questions that you send our way.
Yeah, so we've got a few questions already. And for anyone watching, feel free to put any more questions in the chat. We'll be monitoring that, or free to tweet at us or use other social media platforms to reach out. So one of our first questions is, how do you guys organize? It seems like there's a lot of different things going at the same time. How do the shifts work?
Yeah, no, great question. So we organize into different groups that specialize in different observations and measurements. So it starts really with the physical properties, and they're taking any of the density measurements in general. And the core flows through each of the groups, and they work on their respective specialty. within within the greater goal of the scientific objectives of the expedition. In terms of organizing, it is we each have a counterpart that works the other 12-hour shift. So when we're sleeping, they're up. So 24 hours a day, there is core being drilled and being described and measured. You guys have anything else to add to that?
No, we didn't really say the chief function of the fossils, the paleontology on board, is to tell us what the age of the sediments are. As I said, not this stuff, but when we're drilling sediments, each different species will tell you how many millions of years ago it has accumulated. So that's the primary thing. So the paleontologists actually get the very first sample before any of the other analyses are done to give a guide as to what our estimate of the age of the sediment is.
That's right. Sorry about that. Didn't mention the most important.
Great. Okay, another question we have is, how many samples are you taking, or essentially how many meters of core do you hope to get on this expedition?
Oh yeah, well, we're drilling back into likely the Cretaceous on this expedition, maybe even deeper in time. So we're talking up to 100 million years, or a little less, a little more. In terms of the samples that we're taking, while we're on the ship, we take a limited number of samples just for shipboard measurements. So that may be anywhere from 5 to 25 or so per core, and that's per 10 or 9.5 meter interval. Sometimes if there's intervals that we're really interested in, there might be a little more samples taken once it's discussed with co-chiefs. But after the expedition in the spring next year, we will be all getting together, hopefully, in Bremen, Germany, to go to the core repository, where we'll have a sampling party, and we'll take probably thousands of samples in about a week. So we'll all work together and pull out all the cores we drilled from the fridges and sample away.
And so, in related to that, all these cores will be continued to be used in the future then?
Yes, that is the goal. So when we split the core, we have one working half that lays out on the table, and we sample off that working half. When samples are requested and at the sampling party, we'll sample primarily from the working half. We take the other half and we archive it. So we hope to preserve that core for long-term future use, and to have a record of everything that's been drilled on IODP expeditions.
Great. Let's see, I think those are all the questions we currently have. Do you guys have anything else for us?
No, the one thing I should say is that it's really nice. Some really nice things being on board is that the food is great. They feed us often and they feed us well, and we have access to 24-hour soft serve ice cream and cookie breaks, and they bring us little cheeses, and it's pretty nice. And because we're working 12-hour shifts, we don't have to worry about things like laundry or anything like that. So they really take care of us in terms of the staff, and it makes doing the long days a little bit easier.
Great, that's great to hear. Well, thank you all for taking the time out of your busy science schedule to come talk to us and explain what's going on this expedition. For those of you who
Thanks, Mara.
for those of you who are joining across the interwebs, you can continue to send us questions and we'll answer them afterwards as we can. So thanks to everyone.